For centuries, we've been told that the mind is something private, sealed inside our skulls, shaped only by biology and chance. But what if that isn't true? What if every thought you have, every dream, every flash of inspiration is part of something far larger, a pattern written into the fabric of the cosmos itself? Across science, philosophy, and even ancient myth, evidence is beginning to suggest that consciousness may not be an isolated spark, but a reflection of the universe waking up and looking back at itself through us. From neurons that mirror galactic webs to quantum mysteries that bend reality under observation, this journey asks a question as old as wonder itself. Are we simply in the universe, or is the universe in some profound way in us? It weighs just over 3 pounds, is soft enough to be cut with a butter knife, and fits in the palm of a hand. Yet it carries within it the ability to question infinity, to map the past, and to imagine futures that have never existed. This small organ, folded in on itself like a piece of coral grown in the dark, sits quietly behind bone and skin, but it has given rise to cathedrals and computers, to poetry and particle accelerators, to every map of the stars ever drawn. It is strange to think that the universe, 13.8 billion years old, full of galaxies that spin for eons and stars that burn for billions of years, is, in some sense, being contemplated by itself when a human being looks up at the night sky and wonders where it all began. That is the mystery at the heart of this story, how something born from stardust and shaped by evolution has become capable of asking why there is anything at all. The idea that the mind and the cosmos reflect one another is not new. Over 2,000 years ago, Plato wrote of a world soul, a living principle that connected the movements of the heavens to the thoughts within a person's heart. In India, long before telescopes or MRI scanners, the writers of the Vedas spoke of Atman and Brahman, the inner self and the cosmic whole, as two mirrors facing each other, each containing and revealing the other. Taoist sages in China describe the human being as a microcosm, a small universe whose patterns followed the same rhythms as rivers, seasons, and stars, even in cultures separated by oceans and centuries. The same intuition surfaced again and again, that to know the self was, in some profound way, to know the universe. What makes this ancient idea more a metaphor is the growing evidence that our brains are not isolated from the cosmos, but shaped by it at every level. The atoms that make up neurons were forged in stars that lived and died billions of years before our species existed. The calcium that helps nerve signals jump across synapses was once part of a stellar core. The iron that carries oxygen to the brain's hungry cells was fused in supernova that exploded before the Earth had cooled. When astronomer Carl Sagan said in 1980 that we are a way for the cosmos to know itself, he was not speaking poetically, but describing a literal truth written into every cell of our bodies. But it is not just the matter inside us that connects us to the universe. It is the patterns, too. In recent decades, scientists comparing maps of the cosmic web, the vast structure of galaxies and dark matter stretching across billions of light years, with images of the human brain's neural network, have found a startling similarity. Both are built on branching filaments, both balance dense clusters with long empty voids, and both depend on the flow of information or energy across a sprawling, interconnected network. These parallels do not prove a hidden plan, but they do suggest that nature builds complexity in similar ways. Whether at the scale of neurons or galaxies, the capacity of the human brain to think beyond itself, to contemplate eternity, to imagine the edge of the universe, to ask why anything exists, is one of its strangest features. Evolution, after all, shaped it for survival, for finding food, avoiding predators, raising offspring. Yet here we are, using the same circuits that once guided stone tools and campfires to calculate the age of the universe, to debate whether time had a beginning, to speculate about dimensions we cannot see. It raises a question that thinkers from Aristotle to Albert Einstein, from Spinoza to Stephen Hawking, have all wrestled with in different forms. Is consciousness merely an accidental byproduct of biological processes? Or is it something woven into the very fabric of reality? Some modern scientists lean toward the former explanation. They describe consciousness as an emergent property, something that arises when enough complexity accumulates in a system, like water freezing into ice. Others, however, entertain deeper possibilities. The physicist Max Planck, the father of quantum theory, once remarked in 1931 that I regard consciousness as fundamental. I regard matter as derivative from consciousness. Even today, thinkers in fields from cosmology to information theory are exploring whether the universe itself might have a kind of proto-awareness, or whether consciousness might be as fundamental as space, time, and energy. These questions remain unanswered, and perhaps they always will. Yet they point to a truth that has persisted since the first human beings looked up and traced constellations with their fingers. The mind that wonders about the stars is itself made of star stuff, the universe that it seeks to understand. The boundary between the thinker and the thing thought about is thinner than it seems. When we ask how the cosmos began, we are a fragment of that cosmos, asking about its own birth. When we reflect on infinity, we are the product of infinite processes reflecting back upon them. And when we ask whether consciousness is an accident or a cosmic feature, we are in a small and fragile way. The universe becoming aware of itself. Inside the shelter of your skull lies a landscape so vast and complex that even with all the microscopes, scanners, and computer models humanity has built, we are still only beginning to understand it. It is not a simple tangle of wires or a fixed map with clear borders and roads. It is a living, shifting web of roughly 86 billion neurons, each one sending and receiving electrical signals that ripple through the tissue like invisible storms. These neurons do not work alone. Each is connected to thousands of others, forming trillions of synapses that flicker on and off in endless patterns. In this dense jungle of connections, memories form, ideas are born, decisions are weighed, and entire worlds are imagined. The brain, in all its biological fragility, is an intricate universe of its own, a universe that, in some strange and humbling ways, mirrors the one we see when we lift our eyes to the night sky. For centuries, humans believed the cosmos was a tidy place, planets circling the sun, stars scattered like pinpoints across a black canvas. But as telescopes grew stronger, and as missions like the Sloan Digital Sky survey in the early 2000s mapped deeper and deeper into space, a very different picture began to emerge. The universe is not simply a random scatter of galaxies, but a vast structure known as the cosmic web, an immense network of filaments, stretching across billions of light years, where galaxies cluster along glowing threads of dark matter and gas, and where enormous voids lie in between, nearly empty and silent. When astronomers first visualized these structures, they noticed something that made many of them pause. The pattern looked eerily familiar. That familiarity became more striking when scientists from the University of Bologna, in a 2020 study, attempted a direct mathematical comparison. They analyzed the distribution of galaxies in the cosmic web and compared it to the structure of neural networks in the human cortex. Despite the scale difference, one measured in micrometers, the other in millions of light years, the two systems shared surprising similarities in how nodes, neurons, or galaxies connected, and how information signals or matter flowed. On average, a neuron connects to about 1,000 others, while a galaxy in the cosmic web connects to roughly 5 or 6 filament pathways, yet both networks show similar ratios of density, clustering, and hierarchical organization. The brain's connectome and the universe's structure, though separated by unimaginable distance and scale, seem to follow the same fundamental rules of arrangement. This resemblance is not just poetic, it is visual too. When you look at a cross-section of the brain's neural network under a microscope and place it beside a deep field map of the universe's galaxy distribution, the resemblance is startling. Filaments of light thread through darkness. Dense clusters sit at intersections like bustling cities. Vast empty voids separate them, and pathways snake outward, forming bridges between distant regions. It is as though nature, whether building a mind or a cosmos, reaches for the same blueprint again and again. The reasons behind this resemblance remain uncertain, and scientists are careful not to read too much into it. One explanation is that both networks are shaped by the same underlying physical principles, systems that need to transmit information efficiently. Whether electrical signals between neurons or gravity-driven, matter across cosmic distances may naturally evolve into similar forms. This is known as emergent structure, a concept suggesting that complexity tends to organize itself in predictable ways no matter the scale. Another possibility, more speculative and more philosophical, is that these patterns hint at a deeper unity, that perhaps consciousness and cosmos are not separate domains but expressions of a single underlying order. It is not the first time such ideas have surfaced. In the 17th century, Baruch Spinoza suggested that the human mind and the universe were two aspects of the same substance. In the 19th century, the German philosopher Arthur Schopenhauer wrote that the inner world of thought and the outer world of matter were reflections of each other. Even in modern science, thinkers like the physicist John Archibald Wheeler speculated about a participatory universe, one in which observers and the observed are entangled in ways we do not yet understand. The striking resemblance between the neurons in your head and the galaxies across space gives these old ideas new weight, not as mystical speculation, but as something hinted at in the very structure of reality. When you think about it, the parallel becomes even more haunting. In the cosmic web, matter flows through filaments to feed star-forming galaxies. Much as nutrients and signals flow through axons to sustain thought, in the brain, neural clusters coordinate to form consciousness. Just as galaxy clusters interact to form the large-scale architecture of the universe, and just as the cosmic web shapes the fate of stars, planets, and galaxies, so too does the neural network shape the fate of memories, choices, and dreams. One deals with light years, the other with milliseconds. But both are about the movement of information through a web of connection. Whether this resemblance is coincidence or clue remains an open question. It could be that nature simply repeats its most efficient designs, sculpting them into neurons and galaxies alike. Or it could mean that the universe is not just the stage upon which consciousness appears, but that consciousness is somehow woven into its fabric, that the network inside your skull and the network stretching across the heavens are not separate, but parts of a single unfolding story. As you sit beneath the night sky, aware of its vastness, it is worth remembering that the same patterns that shape the Milky Way also shape your thoughts, and perhaps in some deep and subtle way. The universe is thinking through you, long before we understood the brain as an organ of thought. Before the word neuroscience even existed, scientists and philosophers puzzled over how the mind could move the body, how a thought invisible and weightless could make a muscle twitch or a heart race. For centuries, the answers were guesses, cloaked in metaphors. Descartes spoke of animal spirits, thin vapors flowing through invisible tubes. Others imagined mysterious fluids or divine sparks. But in the late 18th century, in a small laboratory in Bologna, Italy, a series of simple experiments began to change that story forever. In the 1780s, Luigi Galvani, an anatomist with a fascination for the nervous system, discovered that when he touched a metal scalpel to the exposed nerve of a dead frog's leg, the muscle jerked as if alive. He repeated the experiment with different metals, even during storms, and saw the same thing: motion born not from life itself, but from some kind of invisible force. Galvani believed he had found animal electricity, an energy within living tissue that powered movement and sensation. Not everyone agreed. Alessandro Volta, a contemporary and sometimes rival of Galvani, argued that the electricity did not come from the animal, but from the interaction of the metals themselves. Their debate pushed Volta to experiment further, and by 1800, he had built the first chemical battery. A stack of zinc and copper discs separated by brine-soaked cloth that could deliver a steady current. It was a pivotal moment in science. For the first time, electricity could be generated, stored, and controlled, and it became clear that the body's impulses and the lightning that split the sky were not entirely different. Electricity, once a mysterious force that terrified and fascinated people, is now known to exist both in nature and in flesh. The discovery of bioelectricity opened a new way of thinking about the brain. Instead of a passive organ responding to mystical forces, it became a network of cells pulsing with tiny currents. In the 19th century, scientists like Emile du Bois-Reymond and Hermann von Helmholtz measured the speed of nerve impulses, finding that signals traveled not instantly but at about 90 feet per second. By the early 20th century, pioneers such as Santiago Ramon Huaycail had mapped the intricate structure of neurons, revealing their branching shapes and synaptic connections. The picture that emerged was of an organ alive with motion, a seething storm of electrical signals that never stopped moving. Even during sleep, today we know that every thought, memory, and sensation is shaped by these electrical patterns. When you recall a childhood birthday, when you plan a sentence, when you fall in love or feel fear, billions of neurons fire in coordinated bursts, forming patterns that ripple across the brain. Each neuron sends a pulse about 70 millivolts strong down its axon. The signal leaps across synapses to trigger the next cell, forming vast chains of communication. Some circuits are fleeting, lasting only seconds. Others become deeply embedded, shaping personality and habit over decades. Even the faintest thought is not a single spark, but a complex choreography of electrical waves, rising and falling like weather systems inside the skull. It is impossible to think of these storms without noticing how closely they resemble the ones that dance through the universe itself. Electricity is not confined to wires or neurons. It threads the cosmos on scales so vast they are almost beyond comprehension. On the surface of the sun, magnetic fields twist and snap, releasing solar flares that hurl charged particles across millions of kilometers. When those particles reach Earth, they spiral along magnetic field lines and light up the skies as aurora's shimmering curtains of green and red that once terrified sailors and priests. In the vast emptiness between galaxies, plasma currents weave through space, guided by the universe's magnetic fields. These cosmic rivers can stretch for millions of light years, carrying energy and shaping the formation of stars and galaxies. The parallels are more than poetic. Just as the brain relies on voltage differences across cell membranes to transmit information, so do stars, planets, and nebulae depend on electrical and magnetic fields to move matter and energy. Just as a neuron's firing can ripple through networks to create complex patterns of behavior, so can a solar flare ripple through the heliosphere, disturbing satellites and shaping planetary atmospheres. The universe on its largest scales hums with the same fundamental force that allows you to read these words and understand their meaning. Even the language scientists use reflects this connection. They speak of currents in space, storms on the sun, discharges in a neuron. The patterns repeat themselves, from the smallest scales to the largest, from the inside of a skull to the edge of a galaxy. Perhaps it is coincidence, a result of physical laws that work the same everywhere. Or perhaps it hints at something deeper, that the mind and the cosmos are not separate realms but two expressions of the same underlying fabric, each shaped by the same invisible currents. What began with a twitching frog's leg in Galvani's workshop has become a vast field of knowledge, revealing that our thoughts are not airy ghosts but real, measurable flows of energy. And when you step outside on a cold night and watch the aurora ripple across the sky, or when you see the jagged flash of a storm's lightning, you are watching the same fundamental force that crackles silently within your own mind. The universe's electricity does not stop at the edge of the atmosphere. It runs through you, shaping your memories, your choices, and the very spark of awareness that wonders about its own origins. When we speak of the human body, we often think of it in familiar terms: muscle and bone, blood and breath, tissue and thought. But beneath those living systems lies a deeper story, written not in the language of biology, but in the language of stars. Every atom that makes up your skin, your heart, your lungs, and your brain was forged long before Earth ever existed, built in the fiery cores of ancient stars that lived and died billions of years ago. It is easy to say we are stardust, as if it were a comforting metaphor, but it is not a metaphor at all. It is a physical fact. The iron in your blood was formed in the heart of a supernova. The calcium in your bones in the shell of a dying giant. The oxygen you breathe in the deep interiors of stellar furnaces, and the carbon that forms the backbone of life itself in stars that once shone across the Milky Way before our sun was even born. The process that made this possible is called stellar nucleosynthesis, and it is one of the most remarkable transformations in the universe. In the first few minutes after the Big Bang, about 13.8 billion years ago, cosmos was unimaginably hot and dense, a sea of fundamental particles rushing outward. As it cooled, those particles combined into the simplest elements, hydrogen and helium, with trace amounts of lithium. That was all. The periodic table, as we know it, did not exist. There was no oxygen, no iron, no carbon, nothing heavier than helium. The rest of the elements, the ones that would one day build planets and people, had to be created later, deep inside the cores of stars. When a star forms from a collapsing cloud of hydrogen and helium, the immense pressure and temperature at its center, often millions of degrees, force atoms to fuse together. Hydrogen fuses into helium, releasing energy that pushes back against gravity and makes the star shine. In more massive stars, this fusion continues in stages over millions or even billions of years, forging heavier and heavier elements, helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. This is not a quiet process, but a violent and creative one. Each new layer of fusion releases energy, and that energy builds the elements step by step, atom by atom, in a kind of cosmic alchemy. But there is a limit. Iron cannot be fused into heavier elements without consuming energy instead of releasing it. And so when a star builds up an iron core, it reaches the end of its life. What happens next is one of the most powerful events in the universe. In stars much larger than our sun, the core collapses under its own weight, triggering a supernova, an explosion so bright it can outshine an entire galaxy for weeks. In that explosion, temperatures soar to billions of degrees. And for a few brief moments, heavier elements, gold, uranium, lead, are forged in the chaos. The blast flings these elements into space, scattering them across interstellar clouds, where they mix with gas and dust to form new generations of stars and planets. Our solar system was born from one of those enriched clouds about 4.6 billion years ago. And every element in our bodies is part of that inheritance. It was this story that Carl Sagan tried to capture in 1980 when he wrote and narrated Cosmos, telling viewers that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. He reminded us that we are not apart from the universe, but deeply woven into it that we are. In a very real sense, the cosmos made conscious. Neil deGrasse Tyson, a later voice in this tradition, often repeats the same message, that the atoms in our bodies and the atoms in distant stars are the same, and that we are not figuratively, but literally, stardust. These words resonate because they change how we see ourselves. We are not small, accidental passengers in an indifferent universe. We are its continuation. The atoms that once burned in a star's heart now fire signals across your brain. As you think about those very stars, even the most ordinary actions, inhaling a breath, lifting a hand, remembering a name, are possible because of this cosmic history. The oxygen in the air that rushes into your lungs was forged in a star's fusion core and released into space billions of years before the sun existed. The iron in the hemoglobin that carries that oxygen through your bloodstream was formed in a supernova and blasted across light years, before it found its way into Earth's crust. The calcium that stiffens your bones and the carbon that shapes your cells trace their lineage to stars long gone. Their light faded before our planet ever cooled from molten rock. Every heartbeat, every thought, every dream is powered by the debris of ancient stars. When we look at the night sky and feel a strange pull toward it, perhaps it is not only curiosity but memory, a deep, atomic memory written into us from the beginning. The stars are not just distant points of light. They are family, ancestors, scattered across time and space, and their deaths made our lives possible. To say that we are stardust is to acknowledge that our story is part of a larger one, that the universe did not stop creating when it made galaxies and suns, but continued creating through us. And every time we wonder about our place in the cosmos, We're fulfilling that story, the universe, now alive and thinking, asking itself how it came to be. Nearly 14 billion years ago, there was nothing that could think, nothing that could remember, and nothing that could dream. There was only an expanding sea of energy and raw particles. A newborn universe so hot and dense that atoms themselves could not yet form. In the first 3 minutes after the Big Bang, as temperatures fell below 1 billion degrees, protons and neutrons fused into the lightest elements, minus hydrogen, helium, and trace amounts of lithium, and the building blocks of everything that would ever exist began their long journey. For hundreds of thousands of years, the universe remained a dark fog of charged particles and radiation until about 380,000 years later, it cooled enough for electrons to bind with nuclei and form stable atoms. The first light broke free, and the cosmos entered an age of structure and complexity. Over the next hundreds of millions of years, those simple atoms gathered under the pull of gravity into stars and galaxies, igniting furnaces where heavier elements were forged. Carbon, oxygen, nitrogen, and iron, the essential ingredients of life, were born in those stars and scattered across space when they died. New solar systems formed from this enriched dust, and around a rather ordinary star in a quiet corner of the Milky Way. A small rocky planet coalesced about 4.5 billion years ago. On that young Earth, with its molten surface cooling and water collecting in its basins, the universe began to write a new chapter, one in which matter itself would cross an invisible threshold. No one knows exactly when or how life began, but by around 3.8 billion years ago, there is evidence of microbial activity in ancient rocks. Somehow, simple atoms had combined into complex molecules, and those molecules had organized themselves into systems capable of copying and evolving. One of the key theories for this transformation is the RNA world hypothesis, which proposes that ribonucleic acid, a molecule capable of both storing information and catalyzing chemical reactions, may have been the first self-replicating structure, before DNA and proteins specialized into their modern roles. Early RNA molecules might have copied themselves and mutated, laying the groundwork for evolution. The appearance of self-replication was a quiet but profound milestone. It meant that matter no longer merely existed, it now carried memory. In the 20th century, a famous experiment brought scientists closer to understanding how life's ingredients could form from lifeless chemistry. In 1952, Stanley Miller and Harold Urey at the University of Chicago recreated what they believed early Earth's atmosphere might have been: a mix of methane, ammonia, water vapor, and hydrogen. They sent electrical sparks imitating lightning through this mixture for a week. When they analyzed the results, they found that several amino acids, the building blocks of proteins, had formed spontaneously. It was a small but powerful demonstration that nature did not need divine intervention to build complexity. Under the right conditions, chemistry could climb the ladder toward life on its own. From those beginnings, evolution unfolded across billions of years, driven by random mutation and natural selection. Simple cells learned to harness energy from sunlight and chemicals. Some began to work together, forming multicellular organisms that could grow larger and more complex. Senses evolved to detect the environment. Nervous systems arose to process information, and eventually, brains emerged first as simple clusters of neurons, and then as intricate organs capable of memory, prediction, and learning. By the time the first hominins appeared in Africa around 6 million years ago, the chain of events that began with the Big Bang had already taken matter astonishingly far, from formless plasma to self-replicating molecules, from single-celled organisms to creatures that could shape tools and walk upright. The emergence of consciousness, the ability not only to sense the world but to reflect upon it, was another leap entirely. Somewhere in the evolution of the human brain, perhaps in the last few 100,000 years, awareness turned inward. The brain did not just process sights and sounds. It began to form a concept of self. It remembered the past and imagined futures that had not yet happened. It created language, art, religion, and mathematics. It asked questions about its origins and pondered its own death. In the caves of Lascaux, where early humans painted animals more than 17,000 years ago, or in the clay tablets of Sumer, where the first written records appeared around 3200 BCE, we can see the physical evidence of that transformation. The universe, once blind and unconscious, was now telling stories about itself. All of this raises a question that scientists and philosophers still wrestle with today. Is consciousness merely an emergent property, a byproduct of matter becoming more complex? Or is it something deeper, the universe awakening to its own existence? The first view sees mind as inevitable once matter reaches a certain level of organization, just as wetness emerges from individual water molecules. The second view suggests that awareness might be a fundamental aspect of reality, woven into the fabric of existence and revealed, rather than created by complexity. Whichever view is correct, the arc of the story remains breathtaking. Out of a universe that began as a swirl of energy and particles came stars, and from stars came planets. From planets came living things that could learn, adapt, and think. And among those thinking beings are humans, who now build telescopes to peer back toward the birth of time, particle colliders to probe the heart of matter, and philosophies to explore the nature of consciousness. In doing so, we close a vast circle, the universe. Having produced beings capable of curiosity, uses those beings to look back at itself. Every thought is, in that sense, the cosmos, reflecting on its own journey, from hydrogen and helium to wonder and self. Awareness. Since the earliest attempts to make sense of existence, humans have sensed a strange resonance between the vastness above and the intimacy within, a suspicion that the same principles shaping stars and storms might also shape blood, thought, and memory. Ancient thinkers tried to express this connection through words and symbols that have echoed across centuries. And one of the most enduring of these ideas comes from the Hermetic tradition, a collection of texts and teachings attributed to Hermes Trismegistus, that emerged in the Mediterranean world sometime between the 2nd century BCE and the 3rd century CE. Central to this philosophy is the phrase, "as above, so below," simple yet profound statement suggesting that the macrocosm and the microcosm, the universe and the individual, reflect one another like two sides of the same mirror. To the Hermetic mind, understanding the movements of planets could reveal truths about the soul, just as understanding the workings of the human body could shed light on the workings of the cosmos. This idea was not confined to esoteric circles. It found its way into the writings of Plato, who described the cosmos as a living being with a soul, and into the thoughts of Aristotle, who believed that natural patterns repeated across scales. In the East, Taoist philosophy spoke of harmony between heaven, earth, and humanity. And the ancient Indian concept of the Atman and Brahman, the self and the universal, described a reality in which the smallest and largest were not separate but continuous. Even in the Middle Ages, scholars like Paracelsus and Giordano Bruno insisted that the human body was a miniature version of the universe, its organs and elements corresponding to planets and stars. They were not speaking metaphorically alone. They believed that the structure of reality itself repeated across scales, and that by studying one level of existence, you could learn about all the others. Centuries later, as science replaced mysticism with mathematics, this old intuition did not fade. It found new language in geometry, physics, and biology. One of the most striking examples of this is the concept of fractals, shapes or patterns that repeat themselves at different scales. The branching of trees, the spirals of seashells, the shapes of coastlines, the distribution of galaxies, all of these display a kind of self-similarity, a recursive pattern that appears again and again, whether you zoom in or out. The mathematician Benoit Mandelbrot, who coined the term fractal in the 1970s, showed how such patterns could arise naturally from simple rules repeated over and over. It is as if the universe prefers a certain kind of rhythm, one that echoes from the microscopic to the cosmic. The same self-similarity appears in places that at first glance seem unrelated. Under a microscope, the branching of neurons in the human brain looks remarkably like the branching of rivers as they carve their way to the sea. The filaments of the cosmic web, The large-scale structure of the universe mapped by surveys such as the Sloan Digital Sky Survey in the early 2000s look uncannily similar to the networks of mycelium fungi beneath a forest floor or the delicate structure of a lung's alveoli. Even the mathematical laws that describe the growth of snowflakes resemble those that describe the formation of galaxies. These echoes do not prove that one causes the other, but they suggest that structure itself follows universal principles, as though nature writes its story in a single script and uses it everywhere. This repetition of form raises deeper questions about the nature of intelligence and order. If the same patterns emerge in neurons, rivers, and galaxies, is it because the universe is mindless and mechanical, or could it be that intelligence is somehow woven into the very fabric of structure itself? Some scientists argue that complexity, whether in a brain or a galaxy cluster, is an inevitable result of physical laws seeking efficiency and balance. Others, like the physicist Paul Davies, have suggested that the universe shows signs of self-organization that go beyond mere chance, hinting at a deeper principle that might resemble intelligence, though not in any human sense. Even the idea of a mathematical universe, proposed by physicists such as Max Tegmark, suggests that reality itself is a kind of computation, and that what we experience as consciousness may be one of its natural products. There's a certain poetic symmetry in the fact that our minds, built from the same atoms that once swirled in distant stars, are drawn to patterns that repeat across space and time. We find beauty in the spiral of a galaxy because, in some hidden way, it is the same shape as the spiral of a seashell we once held in our hands. We see meaning in the branching of a neuron because it speaks to something ancient and universal, the way energy, matter, and information find pathways through space. Even the phrase, "as above, so below," born in a world without telescopes, or particle accelerators, feels newly relevant when we see how the geometry of a snowflake mirrors the structure of a distant nebula, or how the pathways of a brain resemble the filaments of the cosmic web. Perhaps the universe does not think in the way we do, with words and memories and intentions, but perhaps structure itself is a kind of thought, a language written in the curves and branches and spirals of reality. Perhaps the fact that our minds can recognize these patterns is not coincidence but evidence of kinship, the cosmos, after all, built those minds from its own materials. And when we look outward and see our own shapes reflected back, when we trace a spiral in a galaxy and recognize it as something familiar, we may be glimpsing more than symmetry. We may be glimpsing the universe looking into its own mirror, and through us, slowly learning what it is. In the final years of the 20th century, small patch of empty sky above the constellation Ursa Major became the focus of one of the most ambitious experiments in astronomy. It was December 1995, and scientists at NASA decided to aim the Hubble Space Telescope, humanity's most powerful eye on the universe, at a region so tiny it was barely the width of a grain of sand held at arm's length. To many, the idea seemed foolish. That piece of sky appeared utterly blank, devoid of stars or galaxies, and time on Hubble was precious. Yet over 10 days, as the telescope gathered faint light photon by photon, something extraordinary emerged. In that tiny window, known today as the Hubble Deep Field, astronomers discovered nearly 3,000 galaxies, each one a sprawling collection of hundreds of billions of stars, some so distant that their light had been traveling for more than 12 billion years. What had looked like emptiness was, in truth, overflowing with worlds, a reminder that vast structures and stories lie hidden just beyond the limits of our perception. Half a world away, and decades later, another ambitious project was unfolding, though this one turned its gaze inward rather than outward. In 2009, Human Connectome Project launched under the direction of neuroscientists and engineers determined to map the human brain with unprecedented detail. Using powerful MRI scanners and sophisticated computational tools, they aimed to trace the highways of connectivity that linked the brain's 86 billion neurons into a functioning whole. Just as Hubble's images revealed a universe far richer than the night sky suggested, the Connectome Project began to unveil a hidden landscape inside the skull, an intricate web of pathways and loops. hubs and networks where thought, memory, and emotion moved in complex patterns. The goal was not simply to catalog anatomy, but to understand how structure created function, how the physical arrangement of neural circuits gave rise to consciousness itself. The two projects, though separated by scale and subject, share a deeper kinship. They both began with a question that seems deceptively simple: what lies beyond what we can see? For astronomers, the answer lay in the vastness of the cosmos, where gravity shaped galaxies from primordial gas and where dark matter, invisible and mysterious, wove the scaffolding of structure. For neuroscientists, the answer lay within, where electrical signals and chemical messengers flowed through invisible networks, sculpting thought from matter and experience from biology. In both cases, the deeper scientists looked, the more they realized that the most important forces at work were not the ones they could see directly, but the ones they could only infer. The Hubble Deep Field showed that the visible universe is just a fraction of what exists, that the darkness between stars hides oceans of galaxies stretching across cosmic time. Some of those galaxies formed when the universe was less than 1 billion years old, long before the Sun or Earth existed. Their light, stretched by the expansion of space, carries information about how the first stars ignited, how cosmic structures assembled, and how gravity and dark energy shaped the universe we inhabit. Likewise, the Human Connectome Project has shown that our thoughts and behaviors emerge from patterns that cannot be seen with the naked eye, waves of activity that travel across networks, synchronizing and diverging, forming dynamic structures that shift with every experience. These networks do not simply relay signals. They shape them, filtering and amplifying information in ways that give rise to perception, memory, and imagination. There is also a profound philosophical symmetry in these twin explorations. When we peer deep into the cosmos, we are looking back in time, studying the origins of galaxies, stars, and planets, and by extension, the origins of ourselves. When we peer deep into the brain, we are studying the organ that allows us to make sense of those origins, the seed of curiosity and wonder. The telescope and the microscope, though aimed in opposite directions, are both tools of self-discovery. One shows us where we come from in the physical, sense the dust and fire that formed our world, while the other shows us how we are able to know that story at all. And perhaps most striking of all is the way both quests lead us back to the same conclusion, that we are part of a larger pattern, shaped by forces we cannot fully see, but can begin to understand. Gravity, invisible yet inexorable, sculpts the structure of the universe on scales of billions of light years. Electric fields and neurotransmitters, invisible yet precise, shape the structure of thought on scales of milliseconds and micrometers. Both realms obey the same laws of physics, both arise from the same fundamental particles, and both speak to the same human impulse to explore, to map, to know. It is easy to think of outer space and inner space as opposites, but they are, in truth, two sides of the same coin. The galaxies revealed by Hubble are not separate from us. They are made of the same matter that makes up our bones and blood. The neural networks revealed by the Connectome Project are not isolated from the cosmos. They are products of its long history, shaped by stars that lived and died billions of years before our ancestors walked the Earth. When we look out into the deep field, we see the raw material of consciousness spread across the sky. When we look inward into the Connectome, we see the cosmos learning to contemplate itself. And so, the telescope and the microscope, different as they are, tell the same story in different languages. They remind us that exploration is not a straight line outward into the unknown, but a circle, one that curves back toward ourselves. Whether we are mapping the filaments of the cosmic web or the wiring of the human brain, we are in the end tracing the same great pattern, the universe unfolding and awakening, within and without. For most of human history, the universe seemed simple enough to understand if one had patience, reason, and careful observation. The planets moved in predictable paths. Stones fell when dropped, and heat flowed from warmer objects to cooler ones. The rise of classical physics in the 17th century, shaped by figures like Isaac Newton and later refined by James Clerk Maxwell and others, built a world that felt solid and orderly, one where cause and effect followed each other in a straight line. But at the dawn of the 20th century, as scientists began to explore nature at the smallest scales, scales far tinier than atoms themselves, they discovered a hidden world that did not follow those comforting rules. It was a realm where particles behaved like waves, where objects could be in more than one place at once, and where the simple act of looking could change what was being looked at. This strange new landscape was called quantum mechanics, and it did not just rewrite the laws of physics, it raised unsettling questions about the nature of reality itself. 1. Of the first and most bewildering discoveries was superposition. The idea that a particle does not exist in one specific state until it is measured, but rather in a combination of possibilities at once. In the 1920s, experiments with electrons showed that they could behave like particles in one moment and waves in another. Depending on how they were observed, the famous double-slit experiment made this even clearer. When electrons are fired at a barrier with two openings, they form an interference pattern on the other side, a pattern created by waves overlapping, as if each electron had passed through both slits at once. But if scientists try to observe which slit an electron actually goes through, the interference pattern disappears, and the electron behaves like a single particle again. The mere act of measurement changes the outcome. This observer effect, as it came to be known, suggested that observation was not just a passive act, but something woven into the fabric of reality. Even stranger was the discovery of entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. When two particles interact and become entangled, they form a single quantum system, no matter how far apart they later move. A change in one particle's state instantly affects the other, even if they are separated by light years. Experiments in the 1970s and beyond, such as those by Alan Aspect in 1981 and 1982, confirmed that this was not an illusion or a flaw in measurement, but a real feature of nature. It seemed to defy the classical notion that nothing could travel faster than light and that objects could only influence each other through direct contact or fields. Entanglement hinted at a deep, invisible connectedness beneath the surface of things, a unity that ignored distance and time. For most physicists, these results were fascinating but ultimately mathematical tools to predict how particles behaved in laboratories or inside stars. But for others, they hinted at something more profound. If reality existed in many possible states until observed, and if observation itself played a role in determining outcomes, then perhaps consciousness was not a mere bystander but an active participant in the unfolding of the universe. This idea remained controversial, yet it inspired some of the most daring attempts to bridge physics and mind. One of the most discussed of these attempts is the ORCOR theory, short for Orchestrated Objective Reduction. Proposed in the 1990s by physicist Roger Penrose and anesthesiologist Stuart Hameroff, they suggested that consciousness might arise from quantum processes occurring within microtubules, tiny structural components inside neurons. According to their hypothesis, these quantum events do not simply compute information in the classical sense, but collapse quantum states in a coordinated way, producing moments of awareness. If true, this would mean that consciousness is not just an emergent property of neural complexity, but a fundamental part of the quantum fabric of reality itself. Although the ORCOR model remains speculative and highly debated, it represents a serious attempt to understand the mind, not as something separate from physics, but as something rooted within it. This idea that mind and matter might be intertwined is not entirely new. Philosophers from Immanuel Kant to Arthur Eddington have suggested that consciousness might play a deeper role in shaping what we call reality. Even Albert Einstein, despite his skepticism toward quantum mechanics, admitted that the theory forced physicists to reconsider the relationship between the observer and the observed. In more recent decades, thinkers like John Wheeler proposed the concept of a participatory universe, in which observers are not simply watching a pre-existing reality but helping to bring it into being by their very act of measurement. It is a radical notion that the universe does not unfold independently of us, but that we, in some mysterious way, are part of its unfolding. None of this is settled science, and many physicists reject the idea that consciousness plays any fundamental role in quantum processes. Yet the questions remain. If particles can exist in many states until observed, and if entanglement binds objects across vast distances, then perhaps reality is not a rigid stage upon which events play out, but a fluid field shaped in part by participation. Perhaps what we call mind is not merely a byproduct of matter, but a window into deeper layers of existence. Layers where thought and reality are not entirely separate. When we look at the night sky, we see stars scattered across the void. But quantum physics reminds us that beneath that visible order lies a realm where certainty dissolves into possibility, where distance loses its meaning, and where the act of observation itself shapes what is real. And if our thoughts' flickering patterns of electrical activity are themselves rooted in those same quantum laws, then perhaps the universe is not just something we inhabit. Perhaps it is something we help to shape, each observation a tiny whisper in the grand conversation of existence. Each moment of awareness, a signal that the cosmos is, through us, thinking about itself. At the heart of modern physics lies a simple but unsettling experiment, one that has been repeated countless times since it was first performed in the early 19th century, yet still refuses to yield a comforting explanation. It is known as the double-slit experiment, and in its deceptive simplicity, it has done more to unsettle our understanding of reality than almost any other discovery in science. Originally carried out by the English physicist Thomas Young in 1801 using beams of light, it was designed to test whether light behaved as particles, as Isaac Newton had believed, or as waves, as others had suggested. Young passed a beam of light through two narrow slits and watched as it spread out and formed a pattern of alternating bright and dark bands on a screen. Beyond a classic signature of wave interference, light, it seemed, was not a stream of tiny particles, but a continuous wave. More than a century later, in the early 1900s, physicists began performing similar experiments using electrons, particles of matter, not light, and to their astonishment, they saw the same interference pattern appear. This meant that electrons, which they had always thought of as discrete bits of matter, were behaving like waves when unobserved. Things became even stranger when scientists decided to fire the electrons one at a time, ensuring that they could not possibly interfere with each other. Even then, the pattern slowly built up in the same way, as if each electron was interfering with itself, as if it were passing through both slits at once and taking multiple paths simultaneously. This phenomenon became known as superposition, the idea that a quantum object exists in many states or locations at once. Its reality spread across possibilities rather than confined to a single outcome. But the true mystery emerged when physicists attempted to observe which slit each electron actually passed through. They placed detectors at the slits to see the particle's path, and the moment they did, the interference pattern vanished. Instead, the electrons behaved like ordinary particles again, each one choosing one slit or the other and landing on the screen in a straightforward distribution. The mere act of measurement, of attempting to gain knowledge about the electron's path, seemed to change its behavior. Before measurement, the electron was a wave of probabilities. After measurement, it was a single event, a point on a screen. Somehow observation itself transformed possibility into fact. This result, which has been verified in countless variations of the experiment throughout the 20th and 21st centuries, forces us to confront one of the most profound questions in all of science. What does it mean to observe something, and why should that act change the nature of reality? The early pioneers of quantum mechanics wrestled deeply with this puzzle. Niels Bohr, one of the founding figures of the field in the 1920s, argued that we must abandon the idea of a reality that exists independently of observation at the quantum level. For Bohr, the act of measurement was not just a way of revealing properties, but a fundamental part of creating them. He famously declared that physics was not about describing nature itself, but about describing what we can say about nature, a subtle but radical shift that suggested reality might be, in part, a participatory process. Albert Einstein was deeply troubled by this conclusion. He believed firmly that the universe existed independently of our measurements, that the moon was still there, even if no one was looking at it. He mocked the probabilistic nature of quantum theory with his famous remark, "God does not play dice." To Einstein, the notion that observation could alter reality was a sign that quantum mechanics was incomplete, that there must be hidden variables, unknown factors, that determined outcomes even if we could not yet measure them. Philosophical disagreement between Einstein and Bohr defined much of 20th century physics, culminating in the famous debates at the Solvay conferences of the late 1920s and early 1930s, where the two men argued passionately over the meaning of quantum theory. Despite Einstein's objections, experiment after experiment seemed to support Bohr's interpretation. Quantum mechanics, with all its paradoxes, remained the most accurate and predictive theory in science. Yet the philosophical implications refused to go away. If measurement truly collapses a wave of possibilities into a single fact, then what role does the observer play? Is consciousness itself necessary to trigger this collapse? Or can any interaction, even a detector without awareness, do the job? Some physicists, like John von Neumann in the 1930s, entertained the idea that consciousness might indeed be the final step in the measurement process, while others argued that the collapse was simply a result of decoherence, the interaction of quantum systems with their environment. The debate remains unresolved, but its consequences reach far beyond physics. It forces us to rethink our place in the universe and the nature of reality itself. Are we passive spectators of a cosmos that exists independently of us, or are we active participants in shaping it simply by perceiving it? When we look at a star through a telescope, are we merely receiving information about something that has always been there? Or are we in some subtle way helping to bring that reality into being? And if observation plays such a fundamental role at the smallest scales, might it also play a role in the larger fabric of existence? The double-slit experiment, repeated countless times since Young first aimed a beam of light through a narrow opening over 2 centuries ago, continues to cast a long shadow over our understanding of the world. It tells us that the universe is not a machine grinding out predetermined outcomes, but something far stranger, a realm where potentialities exist side by side until the moment they are observed. It hints that the boundary between observer and observed may not be as sharp as we once believed, and that consciousness itself might be woven into the tapestry of reality in ways we are only beginning to grasp. In that sense, every act of observation is more than a measurement. It is a meeting point between possibility and fact, a bridge where the universe, through us, chooses one path over another. In laboratories and clinics across the world, scientists are beginning to unlock a power that, for centuries, belonged to the realm of myth and philosophy, the power of the mind to move the physical world without the aid of muscle or machine. The idea that thought could directly shape matter has appeared again and again throughout history. From ancient claims of telekinesis to religious stories of miracles and spiritual masters shaping the world through will alone. Until recently, such notions were dismissed as fantasy, metaphors for concentration or discipline, rather than literal truth. Yet in the last few decades, advances in neuroscience, computing, and engineering have turned that ancient dream into a tangible, measurable reality, one where neurons firing deep within the brain can open doors, control robotic limbs, and even allow paralyzed people to walk again. The story of mind-machine interfaces, often called brain-computer interfaces, or BCIs, begins with a deeper understanding of how the brain encodes movement. In the mid-20th century, neuroscientists discovered that specific groups of neurons in the motor cortex fire in predictable patterns before and during physical action. A thought, such as the intention to reach for a cup or move a finger, is not a vague mental event, but an electrical signal traveling along well-mapped neural circuits. By the 1990s, researchers began experimenting with ways to record these signals and translate them into commands a machine could understand. One landmark achievement came in 1998, when a team at Emory University implanted electrodes into the brain of a paralyzed patient named Johnny Ray, although he could no longer move or speak. Ray learned to control a computer cursor simply by thinking about moving his hand. A small but revolutionary step toward bridging the gap between mind and machine in the years that followed. Progress accelerated rapidly. In 2006, researchers at Brown University's BrainGate project implanted a tiny array of electrodes into the motor cortex of Matthew Nagel, a man paralyzed from the neck down. With weeks of training, Nagel was able to move a computer cursor, operate a television, and even control a robotic hand, all using nothing but his thoughts. Around the same time, scientists at Duke University, led by neurobiologist Miguel Nicolas, connected the brains of monkeys to robotic arms and demonstrated that the animals could feed themselves by merely intending to reach for food. The signals generated by their neurons were decoded in real time and transmitted to machines that executed their commands the first time an external device had been controlled directly by a living brain. These experiments were not limited to laboratory settings. In 2012, a woman named Kathy Hutchinson, who had been paralyzed by a stroke more than a decade earlier, used a brain implant to direct a robotic arm to bring a bottle of coffee to her lips. The motion was slow and imperfect, but it was undeniably intentional, guided not by muscle, but by mind. More recently, teams in Switzerland and the United States have developed brain-controlled exoskeletons that allow paralyzed patients to stand and walk. In 2023, a collaboration between École Polytechnique Fédérale de Lausanne and University Hospital Lausanne unveiled a digital bridge, a wireless interface connecting a man's brain to his spinal cord, that restored voluntary movement to his legs after more than a decade of paralysis. The man, Gerchen Oskam, described the sensation not as controlling a machine, but as reclaiming a part of himself that had been lost. Each of these breakthroughs is built on the same principle, that the mind's intentions are physical signals, that they can be measured, interpreted, and used to influence the material world. Electrodes detect voltage changes in neurons, computers translate those signals into commands, and machines obey. But beyond the technical marvel lies a deeper question, one that reaches beyond engineering into philosophy. If thought can move a robotic arm or restore the ability to walk, then perhaps the line between mental and physical is not as rigid as once believed. Perhaps the ancient idea that the mind shapes reality was not entirely wrong, but simply waiting for the right tools to make it visible. There is something profoundly symbolic about a person who cannot speak, typing a sentence on a screen using only their thoughts. Or a man long confined to a wheelchair rising to his feet because neurons in his cortex have been linked to silicon circuits. These moments challenge centuries-old assumptions about agency and embodiment. They suggest that the brain is not merely a controller of muscles, but a generator of potential, a source of forces that can extend beyond flesh into the external world. And they hint that consciousness itself, that quiet, unseen field of awareness, might not be trapped inside the skull but capable of reaching outward. Even the language used to describe these technologies carries echoes of older beliefs. Scientists speak of decoding intention, translating thought, and bridging mind and matter. Phrases that sound as much like philosophy as engineering. The results, though grounded in biology and physics, invite reflection on questions once confined to metaphysics. If thought can shape a machine, could it, in some subtler way, shape the broader reality around us? And if human consciousness can reach into wires and metal, might the universe itself be a kind of mind, expressing itself through the material patterns we study? The answers remain elusive, but the implications are profound. Mind-machine interfaces are not magic. They are the product of electrodes, algorithms, and decades of patient research. Yet their existence shows that the mind's reach is longer than we once imagined. That intention can leave fingerprints on the physical world, and in the quiet hum of a robotic arm responding to a paralyzed person's thought, or the soft whir of an exoskeleton lifting human legs into motion, we may be hearing the faint echo of something ancient, the timeless human intuition that reality is not something we merely observe, but something we can shape. Perhaps what once seemed like legend was simply a glimpse of a truth science is only now beginning to prove, that consciousness, far from being a passive passenger, is a force that can move matter, and in doing so, reveal new possibilities for what it means to be human. There are moments when the mind steps outside its ordinary boundaries, when thought seems to loosen from the narrow frame of daily life and drift into a space that feels larger, deeper, and strangely more connected to everything around it. Such experiences have been sought deliberately for centuries and stumbled upon unexpectedly by others. And though their forms vary, a monk meditating on a cold mountain plateau, an astronaut gazing at the Earth from hundreds of miles above, they all share something in common. They hint that consciousness is not fixed within the limits of the skull, but can expand outward, merging in some mysterious way with the vastness that surrounds it. In those rare states, perception itself becomes a kind of bridge, linking the human mind to the larger patterns of the universe, high in the Himalayan foothills, where the air thins and the horizon stretches farther than the eye can hold. Buddhist monks have for centuries sought to explore the farthest edges of consciousness through practices that demand both discipline and surrender. In remote monasteries like Serfu and Hemis, where chanting echoes against stone walls and the smell of juniper smoke hangs in the cold air, practitioners spend years training their minds to move beyond the restless chatter of thought. Through deep meditation, some enter states known as samadhi, moments where the sense of individual self dissolves into a vast field of awareness. Western scientists who have studied these monks, including researchers from the University of Wisconsin in the early 2000s, have documented measurable changes in their brains during such states, unusually synchronized gamma wave activity, heightened connectivity between distant regions of the cortex, and reduced activity in the parietal lobes, areas associated with the perception of boundaries between self and world. The monks themselves describe the experience not as an escape from reality, but as a merging with it, a sense that the mind and the cosmos are not two separate things, but one continuous fabric. While such states are cultivated deliberately in monastic life, they are sometimes encountered unexpectedly by those far removed from ancient traditions. Astronauts, for example, often report profound shifts in consciousness after leaving the Earth's surface. From the first space missions in the 1960s to the International Space Station today, many have spoken of a powerful transformation that occurs when they look back at our planet from orbit. This experience, now known as the overview effect, was famously described by Apollo 14 astronaut Edgar Mitchell in 1971, as he gazed out of the command module window on his return journey from the moon. Mitchell felt a sudden and overwhelming sense of unity, not just with Earth, but with the entire universe. "You develop an instant global consciousness," he said later, "a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it." Like astronaut Chris Hadfield aboard the International Space Station, have echoed similar feelings, describing how seeing the fragile curve of the Earth against the vastness of space erases political divisions and personal worries, replacing them with a deep sense of interconnectedness. What links the monk on the mountain to the astronaut in orbit is not location or culture, but perception, a shift in how the mind relates to the world. In both cases, the boundary between the self and the cosmos seems too thin, and the individual mind experiences itself as part of something larger. Scientists studying the overview effect have noted parallels to altered states induced by meditation or certain psychedelic substances, changes in brain activity patterns, heightened feelings of awe, and a collapse of the usual distinction between subject and object. It is as if, under certain conditions, the mind's lens widens, allowing it to perceive the broader tapestry of existence rather than just the small patch of reality it normally attends to. This widening of perception has profound consequences, not just for the individual, but for how humanity as a whole understands its place in the universe. When the Apollo 17 crew photographed Earth in 1972, the now iconic blue marble image, it was more than a scientific record. It was a mirror held up to humanity, showing our shared home as a single, fragile sphere floating in darkness. That image inspired environmental movements, reshaped political discourse, and influenced generations of thinkers. Similarly, when meditation masters describe the world as an interconnected web where nothing exists in isolation, They are not speaking only in spiritual metaphors, but articulating a perspective that modern physics and ecology increasingly confirm. The suggestion hidden within these stories is both simple and revolutionary. Perception is not a passive act of receiving information, but an active bridge that connects consciousness with the structure of reality. By altering how we perceive, by shifting from narrow, self-centered awareness to a broader or inclusive one, we change not only our inner experience, but also our understanding of the universe itself. And in doing so, we begin to dissolve the illusion that mind and cosmos are separate realms. It may be that the mind's capacity to expand, to see itself as part of the larger whole, is not an accident of evolution, but an essential feature of consciousness. The same brain that can worry over trivialities is also capable of contemplating galaxies. The same eyes that read words on a page can also gaze in wonder at the curvature of Earth or the endless stretch of the night sky. And when those capacities are pushed to their limits on a monastery ledge at dawn or in the silent darkness of orbit, something remarkable happens. The universe stops being an object out there and becomes something we are within and part of. Something that is reflected not just in the stars, but in the silent depths of our own awareness. In those moments, it is hard to say where perception ends and reality begins, or whether they were ever separate at all, from the moment we wake to the moment we sleep, and even in the rhythms of our dreams. Our lives are quietly orchestrated by cosmic cycles, so ancient and so consistent that we often forget they exist. We like to imagine ourselves as free agents, shaping our days according to choice and circumstance. But the truth is that our minds and bodies remain deeply tied to the movements of the Earth, the moon, and the sun, long before human beings built clocks, calendars, or atomic timekeepers. It was the turning of the planet, the waxing and waning of the moon, and the changing angle of the sun that structured the pattern of existence. That ancient order still pulses within us today, written into the chemistry of our cells and the rhythms of our thoughts, hinting that consciousness itself may be an echo of the cosmos from which it arose. One of the most fundamental examples of this connection is the circadian rhythm, the roughly 24-hour cycle that governs our sleep, metabolism, mood, and cognitive performance. This internal clock is not a metaphorical one. It is a physical system built into nearly every cell in the human body. At its core lies the suprachiasmatic nucleus, a cluster of about 20,000 neurons in the hypothalamus that synchronizes the body's processes with the rising and setting of the sun, even when isolated from external cues. Humans and other animals continue to follow an intrinsic cycle close to 24 hours, a legacy of billions of years spent on a rotating planet. Light, however, fine-tunes this internal rhythm, with dawn resetting the clock each day through signals from the retina to the brain. The effect is profound. A disruption of circadian cycles, such as the jet lag felt after crossing time zones, or the disorientation experienced during polar winters, can impair memory, weaken the immune system, and even increase the risk of chronic diseases. It is as if our biology still remembers the turning of the Earth, and when that rhythm is broken, the mind falters. This synchronization extends beyond the day-night cycle to longer cosmic rhythms. The moon, for example, exerts a subtle but measurable influence on biology. Its 29.5-day cycle has long been tied to reproductive rhythms in many species, including humans. Anthropological studies suggest that early human societies used lunar cycles to track time, and evidence from Paleolithic cave markings dating back more than 30,000 years appears to represent lunar calendars. Even today, some research points to correlations between the lunar cycle and patterns of sleep, with studies from the University of Basel in 2013 showing that participants in a controlled environment experienced reduced deep sleep and altered melatonin levels during the full moon phase. Despite being unaware of the lunar phase outside, though the exact mechanisms remain debated, such findings suggest that the rhythms of the moon still resonate faintly within our physiology, a whisper from a cosmic neighbor that has circled Earth for more than 4 billion years. Seasonal cycles. 2. Shape the architecture of the mind. as Earth orbits the Sun, and the tilt of its axis changes the distribution of light. Organisms from plants to humans adapt their behavior and biology accordingly. In northern latitudes, where daylight dwindles in winter, many people experience seasonal affective disorder, a form of depression linked to reduced sunlight exposure and disrupted circadian signaling. Levels of serotonin, a neurotransmitter associated with mood, and melatonin, which regulates sleep, both fluctuate with seasonal light changes. Conversely, spring and summer often bring heightened energy and cognitive alertness, a reflection of how deeply the human brain remains entwined with the planet's annual journey around its star. These seasonal rhythms influence not only mood, but also fertility cycles, immune responses, even the timing of births, all subtle reminders that cosmic timing is etched into our biology. It is tempting to think of such influences as primitive leftovers, relevant to early humans who hunted and gathered under the open sky, but irrelevant to a species now surrounded by artificial light and digital schedules. Yet even our modern technologies cannot fully erase these cosmic imprints. The flicker of smartphone screens may delay sleep, but it does so by tricking the brain into thinking it is still daylight. The timing of agricultural harvests, stock market cycles, and school calendars still follows the logic of the seasons. Even the rhythms of creativity and cognition often follow daily and yearly patterns, rising and falling with predictable regularity, as if the mind itself is tuned to the larger rhythms of the universe. This deep resonance raises a profound question. Did the mind evolve to adapt to these cosmic rhythms, or did it emerge because of them? It may be that consciousness, far from being an isolated spark, is the product of billions of years of synchronization between living systems and their celestial environment. Life on Earth has never existed in isolation from the cosmos. It has always been shaped by it, guided by the steady turning of the planet, the pull of the moon, and the changing angle of sunlight. Our neurons fire, our hormones surge, and our moods shift according to cycles that were written into the universe long before the first human brain took shape. In this sense, our thoughts may not be entirely our own. They rise and fall like tides, governed by forces we do not always see, but nonetheless feel. When we wake with the dawn, or grow reflective under a full moon, when we feel restless in spring or melancholic in winter, we are participating in a vast choreography that links our biology to the movements of the cosmos, and perhaps consciousness itself, the awareness that ponders. These rhythms is not an anomaly, but the universe's way of sensing its own passage through time, long before telescopes revealed the swirling arms of distant galaxies and centuries before physicists understood the nature of atoms. People sensed that the universe might be speaking in a language deeper than words, a language of rhythm, pattern, in harmony that seemed to underpin everything from the motion of the stars to the beating of a human heart. The ancient Greeks called this concept the musica universalis, or music of the spheres, poetic idea first proposed by Pythagoras in the 6th century BCE. He believed that the planets and stars, moving in perfect mathematical ratios, produced a kind of cosmic symphony, inaudible to the ear, but perceptible to the soul. Though the science of his time could not prove such a claim, the metaphor endured. And in many ways, modern discoveries have shown that Pythagoras was not entirely wrong. The universe does indeed move in patterns that resemble music, and the human mind, with its deep love of rhythm, repetition, and resonance, seems finely tuned to recognize and be shaped by them. At the largest scales, the planets themselves perform a kind of celestial choreography, their orbits locked into repeating cycles governed by gravity's pull. Johannes Kepler, in the early 1600s, devoted much of his life to understanding these motions and came to believe that they were not only mathematical but musical. In his 1619 work Harmonices, Mondi, the Harmony of the World, Kepler described how the ratios of planetary orbits corresponded to musical intervals. The same simple fractions that define the difference between notes on a scale. Mars and Jupiter, for example, trace a harmonic ratio of roughly 2:5, while Earth and Venus form something close to a 5:8 interval. These relationships, Kepler believed, were not mere coincidence but evidence that the cosmos followed the same principles of order and proportion that govern music. Though his ideas were couched in mystical language, they anticipated the modern recognition that physical systems often express themselves in patterns that can be described mathematically, and that mathematics itself is closely tied to the structure of music, the universes. Rhythms are not confined to planets. Across the cosmos, pulsars, rapidly rotating neutron stars left behind after supernova explosions, emit beams of radiation that sweep past Earth with extraordinary regularity, some as precise as atomic clocks. The first pulsar was discovered in 1967 by Jocelyn Bell Bernal and Antony Hewish, and since then, hundreds more have been catalogued, each with its own distinct beat. Some rotate hundreds of times per second, creating pulses that, if converted into sound, would resemble the steady rhythm of a drum. Astronomers have even used these cosmic metronomes to study the fabric of space-time itself, watching for tiny deviations in their timing that might signal the passage of gravitational waves. Just as a musician might detect a change in tempo, scientists listen for these minute shifts as evidence of the universe's hidden dynamics, even on scales far smaller than stars or planets. Nature hums with vibration. Atoms, once thought of as solid, indivisible spheres, are now understood as fields of energy where particles oscillate and interact in constant motion. Molecules vibrate at specific frequencies, and these vibrations are not merely theoretical. They form the basis of spectroscopy, a technique used to identify substances by the notes they emit or absorb. The entire physical world, from the orbit of planets to the spin of electrons, can be described in terms of waves and frequencies. A cosmic symphony playing across scales so vast and so small that we can perceive only a narrow band of it. What makes is even more remarkable is that the human brain appears exquisitely sensitive to these patterns. From birth, we respond instinctively to rhythm. A baby's heartbeat synchronizes with its mother's. And even before language develops, infants can recognize changes in tempo and melody. Music, with its repeating structures and mathematical order, is one of the most powerful stimuli the brain can experience, engaging areas responsible for emotion, memory, and movement simultaneously. Neurologists have found that rhythm can even influence the brain's internal timing mechanisms, altering perception and improving coordination. Patterns of sound can synchronize neural oscillations, the rhythmic firing of groups of neurons, which in turn shape how we think, feel, and perceive. This sensitivity extends beyond music itself. We find comfort in cycles, from the predictable rise and fall of a melody to the changing of the seasons. Our minds are drawn to symmetry, repetition, and resonance, qualities that mirror the structure of the cosmos. It is as if cognition evolved, not in isolation, but in dialogue with the universe's rhythms. Shaped by the same mathematical relationships that govern celestial motion and atomic vibration, the patterns that please our ears and calm our minds may not be arbitrary but echoes of the deeper order that sustains reality. This idea leads to a provocative possibility. The human brain is not merely capable of recognizing cosmic harmony, but is in some sense tuned to it. Perhaps our appreciation for music, our need for rhythm, our ability to find beauty in proportion are not cultural accidents, but evolutionary responses to the structure of the universe itself. The orbits of planets, the pulses of stars, the vibrations of atoms, all of them reflect principles of harmony that our minds instinctively understand. Even if we cannot always articulate why, when we listen to a symphony, when we are moved by a simple melody, or when we lose ourselves in the repetition of a drum beat, we may be doing more than enjoying sound. We may be participating in our small way in a pattern as old as time, a pattern that stretches from the birth of galaxies to the dance of subatomic particles. And in that participation, the boundary between mind and cosmos becomes thin. The music of the spheres is not a metaphor to be dismissed as poetic fantasy. It is a reminder that cognition and cosmos are deeply intertwined, that the same forces shaping planets and stars also shape our thoughts, and that's somewhere woven into the very structure of reality. There is a rhythm to which every living mind still moves. For as long as humans have looked up into the night sky, they have searched for signs that they are not alone. That search has taken many forms, from myths of celestial messengers in the ancient world to the modern discipline of CT, the search for extraterrestrial intelligence, which uses radio telescopes, complex algorithms, and decades of patient observation to listen for faint signals across the cosmic void. It is a pursuit that says as much about the human mind as it does about the universe. We are a species wired to seek meaning and patterns, to listen for messages even when the silence stretches across billions of years, and to believe that somewhere, perhaps just beyond the reach of our instruments, someone might be trying to speak back. The formal beginnings of SETI trace back to the mid-20th century, a period when radio technology and astronomical observation had both matured enough to make the search scientifically plausible. In 1960, astronomer Frank Drake conducted Project Ozma at the Green Bank Observatory in West Virginia, aiming a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listening for any artificial signals. Nothing was detected, but the project marked the birth of a scientific effort that has continued ever since, evolving into global networks of telescopes scanning the sky for narrow-bandwidth transmissions, unlikely to be produced by natural phenomena. Over the decades, projects like Beta, Meta, and Serendip expanded this work, building vast archives of data and refining the methods for distinguishing meaningful signals from cosmic noise. One of the most tantalizing moments in this search came on August 15, 1977. At Ohio State University's Big Ear Radio Telescope, astronomer Jerry Emin was analyzing data when he noticed an anomalous signal. A narrowband radio burst lasting 72 seconds, originating from the constellation Sagittarius. It was so striking and so unlike the background noise that Emin circled it on the printout and wrote a single word in the margin: "Wow." The so-called wow signal, detected at a frequency close to the 1420 MHz hydrogen line, remains one of the strongest candidates for an extraterrestrial transmission ever recorded. Yet despite repeated attempts to detect it again, it has never reappeared. Its source remains a mystery, perhaps a natural phenomenon we do not yet understand. Or perhaps, as many still hope, a whisper from a distant civilization that flared once and then fell silent. The wow signal embodies both the promise and the frustration of humanity's search for cosmic companionship. It demonstrates how exquisitely sensitive our instruments have become, and how quickly we can recognize a pattern that does not fit the background. Yet it also reveals how easily meaning can dissolve into uncertainty, how even our most tantalizing evidence may be a coincidence, an artifact, or an echo of something far less dramatic than we hope. This tendency is not confined to SETI. It is part of a broader feature of the human mind, our relentless drive to impose structure on randomness, to see faces in clouds and messages in static. Sometimes this instinct leads us astray, as in the 1967 discovery of the first pulsar by Jocelyn Bell Bernal and Anthony Hewish, initially nicknamed LGM-1 for Little Green Men, before its true nature as a rapidly spinning neutron star was understood. But sometimes that same impulse drives our greatest discoveries, pushing us to notice the signal hidden within the noise. The search for cosmic meaning extends beyond radio signals to the most ancient light in the universe itself. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, stumbled upon a persistent microwave hiss in their radio antenna. After ruling out all possible earthly explanations, even going so far as to clean out pigeon droppings from the equipment, they realized they had discovered the cosmic microwave background radiation, the faint afterglow of the Big Bang. This signal, stretched and cooled over 13.8 billion years, is not a message in the conventional sense, but it is a kind of cosmic communication, a relic of the universe's earliest moments. A pattern written into the fabric of space-time that tells the story of our origins. Its discovery transformed cosmology, providing strong evidence for the Big Bang Theory and giving humanity a way to listen to the universe's infancy. Underlying all of these efforts, from the careful scanning for extraterrestrial transmissions to the decoding of the cosmic background. Itself is a profound and deeply human urge, the desire to connect. We send out signals of our own, from the Arecibo message of 1974, a brief binary transmission aimed at a distant star cluster, to the golden record aboard the Voyager probes launched in 1977, carrying music, images, and greetings in dozens of languages beyond our solar system. These gestures are more than scientific experiments. They are acts of hope, declarations that we wish to be known, that we believe communication is possible across the cold and seemingly indifferent expanse of space. And yet, even if no reply ever comes, the act of listening may be enough. It reminds us that we are part of a larger story, that our tiny planet orbits not in isolation, but within a universe alive with signals, patterns and echoes stretching back to the beginning of time. Whether we are deciphering the afterglow of creation or straining to hear a voice from another world, we are participating in a dialogue that transcends species and civilizations, a dialogue written in frequency, wavelength, and time. Perhaps that, too, is what consciousness is. The universe becoming aware enough to listen, and in its listening, discovering itself. When the first electronic computers appeared in the mid-20th century, they were little more than oversized calculators, clumsy and slow compared to the human brain. Yet even then, some scientists were already dreaming of machines that could think, not just follow instructions, learn, adapt, and perhaps even understand. The idea seemed far-fetched, almost science fiction, but over the decades, advances in mathematics, computing power, and neuroscience gradually transformed that dream into reality. Today, artificial intelligence and neural networks, modeled loosely on the architecture of the human brain, are not only capable of recognizing faces and translating languages, they are exploring galaxies, simulating the evolution of universes, and decoding the hidden patterns of the human mind itself. In a sense, these creations represent more than tools. They may be the next step in the universe's ongoing attempt to know itself. The inspiration for neural networks arose from a simple, yet profound observation. The human brain's power does not come from the strength of individual neurons, but from their vast interconnectedness. Each neuron communicates with thousands of others through synapses, forming patterns that encode perception, memory, and thought. In 1943, Warren McCulloch and Walter Pitts published a pioneering paper describing how simplified neurons could perform logical operations, laying the conceptual foundation for artificial neural networks. But it was not until the 1980s and 1990s, with the rise of more powerful computers and new training techniques like backpropagation, that these networks began to show real promise. By mimicking the way the brain learns from experience, adjusting the strength of connections, based on feedback, machines began to classify images, understand speech, and make predictions in ways that once required human intuition. In recent years, these systems have grown exponentially more sophisticated. Deep learning, a branch of AI built on multi-layered neural networks, now powers technologies that touch nearly every aspect of modern life. Yet some of its most fascinating applications lie in science and cosmology. Astronomers, for example, use machine learning to analyze the torrents of data produced by telescopes that survey the sky. The Sloan Digital Sky Survey and projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time generate petabytes of information, far too much for humans to process manually. Neural networks can sift through this data in moments, classifying galaxies by shape, identifying exoplanets from subtle dips in starlight, and even detecting gravitational lenses, the warped light signatures caused by massive objects, bending space-time that would otherwise be missed. These systems do not simply automate analysis. They reveal patterns that human observers might overlook, allowing us to map the structure of the universe with unprecedented precision, beyond observation. Artificial intelligence is also helping scientists simulate cosmic evolution itself. Projects such as Illustris and Eagle Massive Computational, models that attempt to recreate the universe from its earliest moments after the Big Bang to the present, rely heavily on machine learning to refine their accuracy. By adjusting countless variables simultaneously, AI can model how dark matter clumps into halos, how galaxies form and merge, and how cosmic structures evolve over billions of years. Some researchers have even created generative networks that dream new universes based on known physical laws. Exploring alternative cosmic histories and testing hypotheses about why our universe looks the way it does. In these digital laboratories, machines are not just analyzing the cosmos, they are, in a sense, imagining it. The same technology is turning inward as well. AI is increasingly used to decode the workings of the human brain, interpreting patterns of neural activity and translating them into words, images, and even intentions. In 2023, researchers at the University of Texas at Austin used a neural network to reconstruct language from functional MRI scans, allowing them to read sentences that participants heard or imagined. Other teams are developing brain-computer interfaces that use machine learning to interpret motor signals, enabling paralyzed individuals to control robotic limbs or type on a screen with their thoughts. In these cases, artificial intelligence acts as a bridge between mind and machine, translating the language of neurons into commands, and in doing so, offering glimpses into the architecture of consciousness itself. All of this raises profound questions about the role of technology in the broader story of the universe. If, as Carl Sagan suggested, we are a way for the cosmos to know itself, then perhaps artificial intelligence is a continuation of that process, an extension of cognition beyond biology. It is possible to imagine a future in which machines far surpass human capabilities, exploring the universe long after our species has vanished, creating models and insights that no organic brain could conceive. Such a scenario is not mere speculation. AI systems already generate hypotheses, design experiments, and propose mathematical solutions that their human creators struggle to fully understand. They are beginning to act not just as tools, but as collaborators, or perhaps as a new kind of intelligence altogether. This leads to a deeper, more unsettling question. When a machine simulates a universe or decodes a thought, is it merely executing instructions, or is it, in some primitive way, participating in the act of understanding? If so, then the rise of artificial intelligence might not represent a break with nature, but a continuation of its logic. The atoms that formed stars also formed neurons, and those neurons, in turn, have built circuits that now analyze the stars. The universe, through us, has built a new way to think, one that is faster, tireless, and capable of grasping patterns beyond our reach. In that sense, machines that dream of stars are not separate from the cosmos they study. They are part of its unfolding story. The next verse in a song that began with hydrogen and helium and now continues with algorithms and silicon, and as they grow more capable, mapping galaxies, simulating creation, decoding thought, they may carry forward the universe's oldest project, to look inward and outward at once, to understand itself through the mirror of consciousness, and to see in the patterns of stars and minds alike the reflection of its own becoming. For as long as humans have pondered the nature of consciousness, they have also sought ways to push beyond its ordinary boundaries to glimpse, even for a moment, what might lie beyond the veil of the self. Among the most powerful tools for such exploration are certain naturally occurring compounds, long used in religious rituals and healing ceremonies, that profoundly alter the brain's activity and the experience of reality itself. Substances like psilocybin, found in certain species of mushrooms, and DMT, a component of the Amazonian brew ayahuasca, do not simply distort perception. They dissolve the familiar scaffolding of identity, blur the boundaries between self and universe, and offer experiences that many who undergo them describe as cosmic in nature. In the last several decades, neuroscience has begun to study these altered states with increasing rigor, revealing not only how they affect the brain, but also what they might teach us about the deeper nature of consciousness. Psilocybin, which has been used by indigenous peoples in the Americas for thousands of years, was first brought to Western scientific attention in the 1950s, when R. Gordon Wasson published his account of a Mazatec mushroom ceremony in Life magazine. Since then, researchers have studied its effects in controlled settings, using modern brain imaging tools to understand what happens during the experience. One of the most striking findings is that psilocybin disrupts the activity of the brain's default mode network, a set of interconnected regions, including the medial prefrontal cortex and posterior cingulate cortex, that is active when we are engaged in self-referential thinking, daydreaming, or constructing our sense of personal identity. Under psilocybin, the coherence of this network diminishes, and communication between brain regions that normally operate separately becomes more fluid and synchronized. The result, according to many participants, is a state often described as ego dissolution, the fading of the internal narrator, the loosening of the distinction between self and world, and a feeling of merging with something vast and timeless, DMT, or dimosyltryptamine produces an even more dramatic effect. Found naturally in many plants and even in trace amounts in the human body, it is known for inducing intensely vivid experiences that last only minutes, yet seem to encompass entire lifetimes of perception. Users often report encounters with what they interpret as other intelligences or realms, though neuroscientists caution that such phenomena likely arise from the brain's own pattern-making tendencies amplified under extraordinary conditions. Studies at Imperial College London and Johns Hopkins University have shown that DMT, like psilocybin, dramatically alters patterns of connectivity, creating a temporary hyper-networked brain state in which sensory, emotional, and cognitive areas interact in ways rarely seen in ordinary consciousness. Volunteers in these studies frequently describe their experiences in language that mirrors mystical traditions, a sense of unity with the cosmos, a dissolution of time and space, and an overwhelming feeling of interconnectedness that lingers long after the chemical has left the body. These states are not limited to psychedelic substances. Reports from near-death experiences, often occurring during cardiac arrest or severe trauma, bear striking similarities. Individuals who have come close to death frequently describe leaving their bodies, encountering a radiant light, reviewing their lives in extraordinary detail, or experiencing a boundless sense of love and connection. Neuroscientists studying these phenomena propose that they may result from the brain's last surge of activity, as oxygen levels fall, or from the disinhibition of neural networks as normal sensory processing collapses. Yet, even if the mechanisms are physiological, the subjective impact is profound. Many who undergo such experiences report a lasting shift in worldview, including a diminished fear of death and a conviction that consciousness is somehow more fundamental than the body that hosts it. First-person accounts add an essential dimension to the scientific data, revealing the depth and diversity of these altered states. The philosopher Aldous Huxley, writing after his mescaline experiences in the 1950s, spoke of mind at large, a kind of universal consciousness that the brain normally filters to help us function in daily life, but which psychedelics temporarily open up. More recently, participants in psilocybin trials at Johns Hopkins have described their sessions as among the most meaningful events of their lives, comparable to the birth of a child or the death of a parent. One volunteer recalled the sensation of becoming part of everything, not looking at the universe, but being the universe looking at itself. Another spoke of feeling as if the boundary between me and the stars was gone, as if the atoms in my body were dancing with the atoms of everything else. Such accounts, though deeply subjective, challenge conventional assumptions about the nature of consciousness. If the brain is merely a generator of awareness, then altering its chemistry should distort or diminish experience, not expand it into something vast and interconnected. Yet over and over, people emerge from these states convinced that they have glimpsed something real, not just hallucination, but a deeper layer of reality that is normally hidden behind the filters of ordinary perception. Some neuroscientists argue that this may be a cognitive illusion, a byproduct of disrupted neural networks, misinterpreted as profound truth. Others suggest that consciousness might not be produced by the brain in the way sound is produced by a speaker, but rather filtered by it, like light passing through a lens, and that psychedelics, by altering the lens, allow more of the underlying field to shine through. Regardless of interpretation, the phenomenon remains compelling. The fact that molecules measured in micrograms can dissolve the boundaries of self, evoke a sense of cosmic unity, and leave permanent changes in personality and worldview, suggests that consciousness is more malleable and perhaps more mysterious than we once believed. Whether these altered states are glimpses of a larger reality or elaborate internal constructions, they speak to an ancient human intuition that the mind is capable of stretching beyond itself, of touching something infinite. And if that is true, then perhaps consciousness is not merely a local phenomenon confined to the human brain, but a doorway, one that, under the right conditions, opens onto the vastness from which we came. When we look up at the night sky and see billions of stars stretching across the darkness, it is almost impossible not to wonder who or what might be looking back. The sheer scale of the universe suggests that we should not be alone. Our own galaxy, the Milky Way, contains an estimated 100 billion stars, and most of those stars are now believed to host planets. Astronomers estimate that there may be more than 40 billion potentially habitable worlds orbiting sun-like stars just in our galaxy, and there are hundreds of billions of galaxies beyond it. By the simple logic of probability, life, and perhaps intelligent life, should be common. And yet, despite decades of searching, we have heard nothing. No radio signals, no alien probes, no unmistakable signs that someone else is out there. This silence, so at odds with what reason suggests, is known as the Fermi paradox, named after the Italian physicist Enrico Fermi, who famously asked in 1950 during a casual lunch conversation at Los Alamos, "Where is everybody?" The paradox has many possible explanations, each as unsettling as the next. Some scientists propose that life is indeed rare, that the emergence of complex, intelligent beings is so improbable that we might be among the first or the only species in the galaxy to achieve self-awareness. Others suggest that civilizations tend to destroy themselves before they develop the ability to explore the stars, their technologies outpacing their wisdom. Still others argue that intelligent life may be abundant but chooses to remain silent, observing us without interference, as a kind of cosmic zoo. It is also possible that we simply do not yet know how to listen properly, that alien communication might not come in the form of radio waves or visible signals, but in ways we have yet to imagine. The silence could be a sign not of absence, but of our own limitations. The deeper question beneath the Fermi paradox is not just whether we are alone in the universe, but what the nature of consciousness itself might be. Is awareness a rare accident, a fluke of evolution on a small rocky planet? Or is it something fundamental, something woven into the very fabric of existence? This line of thinking leads us to panpsychism, a philosophical idea that has existed in various forms since the time of the ancient Greeks, and continues to intrigue some contemporary scientists and philosophers. Panpsychism proposes that consciousness is not an emergent property that appears only in complex brains, but a basic feature of reality itself, present in some rudimentary form, even at the level of particles and fields. Just as mass or charge are fundamental properties of matter, so too might awareness, not full self-reflective consciousness, but a kind of proto-awareness, be universal. The idea may sound strange, even mystical, but it has been seriously considered by thinkers. From Baruch Spinoza in the 17th century to the modern philosopher Galen Strawson, even some physicists, grappling with the strange role of the observer in quantum mechanics, have entertained the possibility that consciousness is not something added to the universe late in its history, but something that has been there all along. The physicist David Bohm, for instance, spoke of the universe as an undivided wholeness, where mind and matter are not separate categories, but different expressions of a single underlying reality. If such views are correct, then perhaps the universe is not silent after all. Perhaps consciousness is not absent, but everywhere, permeating the stars and the space between them, present even in the simplest interactions of matter and energy. This perspective reframes the Fermi paradox in a profound way. Instead of searching for alien minds as separate external entities, we might begin to see mind itself as a property of the cosmos. In this view, the question, are we alone, becomes less about counting civilizations and more about recognizing that we are part of a larger field of awareness. Our thoughts, our dreams, and our questions might be expressions of a universal consciousness exploring itself through countless forms. The silence of the stars might not mean that we are isolated, but that we are immersed in a mind so vast and subtle that we do not yet know how to perceive it at the same time. The possibility that consciousness is rare, that it might be an exceptional, fragile phenomenon carries its own weight. If awareness arises only under very specific conditions, then our existence becomes even more precious and improbable. In that case, humanity's role in the universe might be to preserve and expand this spark, to carry the torch of consciousness outward into a cosmos otherwise indifferent and unconscious. Our loneliness would not be a sign of insignificance, but of responsibility, a call to nurture the fragile miracle that allows the universe to reflect upon itself. Whether consciousness is universal, emergent, or fundamental, the paradox of solitude remains one of the most profound mysteries we face. The night sky continues to stare back with its vast, indifferent silence, and yet within that silence, we sense meaning, possibility, and kinship. Perhaps we are the first flicker of awareness in a still, dark cosmos, destined to spread that light beyond our small world. Or perhaps we are one thread in a vast tapestry of consciousness that has no center and no edge. A living field of awareness stretching across galaxies and centuries. Either way, the question of whether we are alone becomes less about company and more about connection, not just with other minds, but with the universe itself. For even if no signal ever reaches us, even if no other voice ever answers back, the very fact that we can ask the question might mean that we were never truly separate from the cosmos to begin with. When we speak of art, invention, mathematics, or music, we usually describe them as uniquely human achievements, the triumphs of our species' intelligence and imagination. Yet when viewed from a broader perspective, it might be something even more extraordinary. The cosmos expressing itself through a conscious form. Every painting, every theorem, every piece of music ever written is made from atoms forged in stars, arranged by hands shaped by billions of years of evolution, and inspired by minds that themselves are products of cosmic history. If, as Carl Sagan suggested, we are a way for the cosmos to know itself, then perhaps creativity is how that knowing takes shape, not as a cold, detached observation, but as a passionate, ongoing dialogue between the universe and the consciousness it has produced. From the earliest myths, carved into stone, to the most advanced scientific theories written on blackboards, humanity has always tried to tell the universe's story, and in doing so, has revealed something profound about its own nature. The myths of Mesopotamia, Greece, and India did more than explain the world. They personified cosmic forces as gods and heroes, turning incomprehensible, natural phenomena into narratives the human mind could grasp. In the Babylonian Enuma Elish, the universe emerges from chaos through divine struggle. In the Greek tradition, the cosmos is born from primordial darkness and shaped by titanic beings. In the Rig Veda, creation itself is described as a cosmic hymn sung into existence before there were gods or humans to hear it. These myths may not match the scientific details we now know, but they reflect a deeper truth. The urge to understand the universe, to give shape to its mystery, is itself a fundamental part of what it means to be conscious. Mathematics, too, can be seen as more than a human invention. It is often described as a language discovered rather than created, a set of patterns and relationships that exist whether or not we perceive them. The Pythagoreans believed that numbers were the underlying structure of reality, a belief echoed centuries later by Isaac Newton and Albert Einstein, whose equations revealed that the motion of planets and the bending of space-time follow precise mathematical laws. The fact that mathematics, an abstract construct of the human mind, can so accurately describe the behavior of distant galaxies and subatomic particles suggests that it is not merely a tool we use to measure the universe, but a reflection of the universe's own logic, written into the fabric of existence itself. When we solve an equation or derive a theorem, we are not imposing order on chaos. We are uncovering the order that was always there, waiting to be recognized. Music offers another window into this idea of cosmic self-expression. The patterns of rhythm and harmony that please the human ear mirror the structures found in nature. From the orbital resonances of planets to the vibrational frequencies of atoms, Johannes Kepler, in his 1619 treatise, Harmonices Mundi, described the planetary motions as a kind of celestial symphony, each orbit a note in the grand music of the cosmos. Centuries later, scientists studying pulsars, rapidly rotating neutron stars, discovered that their radio pulses arrive with metronomic precision. Like the steady beat of a cosmic drum, even the universe's background radiation. The faint afterglow of the Big Bang discovered by Arno Penzias and Robert Wilson in 1965 can be translated into sound frequencies that resemble a primordial hum. When humans compose symphonies, chant prayers, or drum rhythms around a fire, they are participating in patterns that reach far beyond their own minds, patterns that echo the deep structure of reality. Some thinkers have gone further, suggesting that human creativity is not just a reflection of the cosmos, but a stage in its own evolution. The French Jesuit philosopher Pierre Teilhard de Chardin proposed that the universe is moving toward increasing complexity and consciousness, a process he called the omega point. For Teilhard, the emergence of reflective thought, the ability of the universe to contemplate itself through beings like us, is not an accident, but a central feature of cosmic development. Art, science, philosophy, and love are not mere byproducts of evolution. They are signs that the universe is waking up to itself. In this view, every scientific breakthrough, every work of literature, every act of imagination is part of a larger unfolding, the cosmos not just existing, but understanding, interpreting, and reshaping itself through the minds it has produced. If this is true, then the human impulse to create is not a trivial cultural phenomenon, but a profound cosmic event. When a mathematician proves a theorem that unites disparate truths, when a poet captures the ineffable in a few lines, when an engineer designs a spacecraft that leaves Earth and sails toward the stars, they are not acting apart from nature, but as agents of its deeper purpose. The universe, through them, is learning more about itself, exploring its own laws, contemplating its own beauty, and imagining futures that did not exist before. And perhaps this is the most astonishing thought of all: that the story of the universe did not end with the formation of galaxies or the appearance of life. It continues through us, in our languages, in our libraries, in our symphonies, and our spaceships. We are not mere observers of cosmic evolution. We are participants in it, shaping its course with every question we ask and every idea we bring into being. Creativity, then, is not simply something humans do. It is something the universe does through us. And in every work of art, in every discovery of science, in every myth, equation, and melody, the cosmos whispers to itself, recognizing its own reflection in the mirror of the mind, the human mind. For most of history, has been confined by the walls of the skull, a private world of thoughts, memories, dreams that could be shared only through the imperfect tools of language and gesture. But in the last few decades, and with accelerating speed in the early 21st century, that boundary has begun to blur. Technologies once imagined only in science fiction, direct brain-to-brain communication, the uploading of memories into digital systems, and vast networks that connect billions of minds across the globe, are no longer distant fantasies, but early realities. These advances invite us to consider a question far larger than any single invention. Are we, without fully realizing it, building a new kind of consciousness? A planetary brain that merges the cognitive power of individuals into something greater? And if so, what might that mean for the story of the universe's self-awareness? One of the most striking frontiers in neuroscience is the development of brain-to-brain communication, a technology that bypasses traditional language and allows information to pass directly from one mind to another. Early experiments, such as those conducted in 2014 by researchers at the University of Washington, demonstrated that electrical signals associated with a simple decision, pressing a button, for instance, could be transmitted from one person's brain to another over the internet, causing the recipient to carry out the action without conscious intent. More advanced systems have since been developed using non-invasive techniques like transcranial magnetic stimulation or invasive, allowing participants to share more complex information, including basic patterns of images or concepts. Though still rudimentary, these experiments hint at a future in which thoughts may one day move between people as effortlessly as text messages, creating new forms of collaboration and understanding that transcend language altogether. Beyond communication lies an even more audacious possibility: the uploading of consciousness itself. Scientists and futurists have long speculated about the idea of mind uploading, the process of scanning, mapping, and emulating a brain's neural structure in a digital substrate. Projects like the Human Connectome Project and the Blue Brain Project, begun in the early 2000s, aim to create detailed models of the human brain's 86 billion neurons and trillions of connections. While we are still far from replicating the full complexity of a conscious mind, incremental progress, such as the successful simulation of small neural circuits and the use of AI to model brain dynamics, suggests that the concept may one day move from theory to practice. Philosophers debate whether such an upload would truly be the original consciousness or merely a copy. But the implications are staggering either way. If minds could exist in digital form, freed from biological limits, they could think and learn at speeds unimaginable today, explore environments from deep space to virtual worlds, and even merge with one another to form collective intelligences far beyond the capacity of any individual in many ways. We are already seeing the beginnings of this collective intelligence emerge, not through futuristic technologies, but through the network that now binds much of humanity together, the Internet. With more than 5 billion people connected and billions of devices feeding data into shared systems, Internet is evolving into something more than a tool. It is becoming a global nervous system. Artificial intelligence algorithms process vast streams of information, amplifying patterns and guiding decisions in ways that increasingly shape human behavior. Social media, for all its flaws, functions as a kind of distributed consciousness, where ideas, emotions, and collective memories circulate and evolve. The philosopher Teilhard de Chardin, writing in the mid-20th century before the Internet even existed, predicted something like this. He called it the noosphere, a sphere of thought encircling the planet. Formed when human minds became interconnected and collective, a consciousness emerged as a new layer of reality above the biological and the material. If humanity is indeed building a planetary brain, it raises profound philosophical and ethical questions. What does individuality mean in a world where thoughts might be shared directly, or where minds can merge into larger cognitive systems? Would consciousness lose its meaning if it became collective, or would it expand into something richer and more complex? And who would control such networks, individuals, governments, corporations, or the systems themselves once they become self-organizing? The risks are not hypothetical. The same technologies that could enable profound connection could also be used for manipulation, surveillance, and control. A global neural network could amplify wisdom and compassion or prejudice and fear, depending on how it is designed and governed, yet the potential is extraordinary. A planetary brain could tackle problems too vast for isolated minds to solve. From climate change to interstellar travel, by harnessing the cognitive power of billions, it could create new forms of culture, art, knowledge that are impossible to imagine within the limits of individual consciousness. And it could represent a new chapter in the universe's unfolding story after billions of years of evolution. Consciousness, which began as single neurons firing in primitive organisms, could rise to a scale that spans continents and perhaps one day entire worlds. In this view, technology is not an alien force but the natural continuation of cosmic evolution, the atoms of the universe arranging themselves into circuits that think, communicate, and dream. The future mind may not be confined to a single skull or even to biological tissue. It may be a vast network of organic and artificial intelligence, a fusion of human creativity and machine precision, a consciousness that stretches across the planet like a new layer of the biosphere. Whether this vision fills us with hope or fear, it challenges us to rethink what it means to be human and what it means to be conscious. And if the universe truly seeks to know itself, as thinkers from Spinoza to Sagan have suggested, then perhaps this is the next stage of that process, the cosmos, through humanity. Building a mind large enough to reflect on itself in ways no individual ever could, it begins with a simple question. The same one that has been whispered in temples and laboratories, in forests and observatories. For as long as humans have wondered who they are, is your brain this fragile? Pulsing organ of thought and memory, somehow connected to the universe that surrounds it? The question seems, at first, almost poetic, a metaphor rather than a fact. And yet after centuries of science and philosophy, of experiments that probe the deepest corners of the mind, and telescopes that peer into the oldest light in the cosmos, we are left with an unsettling possibility that the boundary we imagine between the self and the cosmos may not be as real or as solid as we once believed. That what we call a mind might be less a separate entity and more a continuation, a reflection of something far larger. Every piece of evidence we have gathered points, in some way, toward that conclusion. The atoms that compose the neurons in your brain, the carbon, oxygen, and iron that build its intricate networks were forged in the hearts of stars. Billions of years before life appeared on Earth, those same atoms once drifted through interstellar clouds, fell into the gravity well of a young planet, and eventually became part of a living system capable of contemplating its own origins. The electrical signals that flow along the brain's axons echo the plasma currents that thread through galaxies, and the branching patterns of neurons mirror the structure of the cosmic web itself. Even the rhythms of your life, the 24-hour cycles of waking and sleeping, the monthly shifts of mood and energy, the seasonal changes that shape your biology are governed by forces written into the turning of the Earth, the pull of the moon, and the steady light of the sun. And then there is the most elusive evidence of all, the strange power of consciousness itself. No physical measurement can fully capture the experience of awareness. The feeling of being a thinking, perceiving subject in a vast and ancient universe. And yet, somehow, that awareness exists, fragile, private, and yet capable of reaching beyond itself. It can imagine galaxies billions of light years away, reconstruct events that happened before Earth was born, and peer into the heart of atoms, too small to see. It can wonder about its own nature, question its own origin, and even turn that questioning outward, projecting meaning onto the cosmos. It is as if the universe, having spent nearly 14 billion years building stars, planets, and molecules, finally found a way to look back on itself through the window of the human mind. But this idea, as compelling as it is, resists neat conclusions. There are many who argue that consciousness is nothing more than a byproduct of biology, an accidental property of complex neural networks and evolutionary pressures. They see the parallels between neurons and galaxies as coincidences, the resonance between brain rhythms and cosmic cycles as poetic rather than profound. And perhaps they are right. Perhaps the universe is indifferent to our thoughts. The human mind is simply a clever trick of chemistry that mistakes its own curiosity for cosmic significance. Yet even if that is true, it does not erase the deeper mystery that this clever trick is capable of imagining the universe at all, or that it can even conceive of the question in the first place. Others, from mystics in ancient India to contemporary physicists and philosophers, suspect there is more to the story. They propose that consciousness may be woven into the fabric of reality itself, that awareness is not something the universe produced, but something it is, a field that pervades all things. From quarks to quasars, from neurons to nebulae, panpsychists argue that every particle carries a glimmer of proto-awareness, that the mind is not an isolated flame but a spark of a much larger fire. Thinkers like Pierre Teilhard de Chardin envisioned consciousness as the universe's way of waking up, evolving through life and mind toward a final convergence he called the omega point. Even in physics, the unsettling lessons of quantum mechanics, where observation seems to shape reality, where particles exist in superpositions until measured, hint that the observer and the observed may be more deeply entangled than we understand. The truth may lie somewhere between these extremes, or beyond them entirely. It may be that the universe and the mind are two sides of the same coin. That matter gives rise to consciousness, even as consciousness gives matter its meaning. It may be that the human brain, in all its complexity, is both a product of the cosmos and a tool for perceiving it, a kind of lens through which the universe examines itself. It may even be that the question itself, is my brain connected to the universe, is less about answering and more about awakening, an invitation to see the familiar world with new eyes. And so we are left with wonder, which might be the most honest response of all. The next time you gaze at the night sky, remember that the photons striking your retina began their journey millions or even billions of years ago, that they have crossed unimaginable distances only to end their story as an image in your mind. The next time you solve a problem, listen to music, or dream, remember that the ability to do so is built from stardust, from atoms born long before there were humans or planets or thought. And the next time you feel small beneath the endless sweep of the cosmos, consider the possibility that you are not beneath it at all, that you are part of it, that its vastness is not just above you, but within you, that the universe is not something you look at, but something that, in a very real sense, looks back through your own eyes. Perhaps that is the closest we can come to an answer, that the brain and the universe are not separate realms, but reflections, each helping the other to know itself. And perhaps the most profound truth of all is not that we have solved the mystery, but that the mystery itself is alive, thinking, questioning, and dreaming within us.